Welcome to Pratham Science Academy classes, and in today's video we are going to discuss Newton's second law of motion and what are its applications. So, what is Newton's second law of motion? Let's uh, write down its definition first. And the Newton's second law of motion has mathematical expression as well. So we'll derive its mathematical formula as well. That is a mathematical expression. So firstly, it's the definition. So it states that the rate of change of momentum is directly proportional to the applied unbalanced force and it takes place in the direction of force. So that's the definition. So that is, we can say that the Newton's second law of motion, it states that the rate of change of momentum, we will also find out or derive its mathematical formula and hence define 1 Newton. So it states that the rate of change in momentum, which we denote by P of a body, is directly proportional. That is, this is a sign for the directly proportional. Is directly proportional to applied force. That is, the force should be unbalanced, or we can write it as with more specific as unbalanced force. Right. Okay, and it takes place in the direction of force. It's obvious. Okay, so this is the definition of the Newton's second law of motion, which states that the rate of change in momentum of a body is directly proportional to applied unbalanced force and it takes place in the direction of the force. Let's try to get and its mathematical expression. Let's try to derive its mathematical expression and hence we will define the SI unit of force. So the derivation of Newton's second law or the mathematical expression we can say okay now from the statement it's given that the force is directly proportional to rate of change of momentum. Okay, that means this unbalanced force is directly proportional to rate. Change in momentum is given by the final momentum minus initial momentum, and rate means it has to be divided by the time. Okay, now the final momentum, we know that the momentum is denoted by P for final momentum, and the formula for the momentum is P is equal to M into B. For final momentum, let's take the final velocity, and for the initial momentum, that would be equal to M, or that is mu, and for time, it's T. Okay, so this becomes F is directly proportional to, let's take M common, V minus U by T. Now we know that change in velocity, that this is the rate of change in velocity divided by time is rate of change of velocity, which is equal to acceleration. So we can write it's directly proportional to M into A, and this is constant. So it becomes equal to, and let's put in some constant here. If you remove the proportional sign, that would be equal to M into A. And this case, the constant of proportionality, if you put K is equal to 1, our mathematical formula from the Newton's second law becomes F is equal to M into A. Now, this is the mathematical expression of Newton's second law of motion From here, we are going to derive the SI unit of force. Now, if let's say mass is 1 kg, and so this mass is 1 kg, and acceleration is 1 meter per second square in SI units. So this is 1 meter per second square. So this force becomes 1 into 1 is 1, so 1 kg meter per second square, and we call it as 1 Newton. So kg meter per second square is denoted by Newton. Now we have the SI unit of force, there is Newton, and we are going to define 1 Newton. So 1 Newton, so we say that, what is the definition of 1 Newton? So we say that force, because it is the SI unit of force, so we will say force is said to be 1 in Newton when it it means force produces an acceleration of 1 meter per second square in a body of mass 1 kg. So that's the definition of 1 Newton. So the question here is, state Newton's second law of motion and derive the mathematical expression for it, which is equal to F is equal to m into A, and hence define 1 Newton. So this is the Newton's second law of motion. This is also called the real law of motion, and why it's called the real law of motion, we will discuss that once we have studied the Newton's third law as well. Okay, so let's move on to its applications. So our first application is why a fielder pulls his hands backwards while fielding the ball. So you might have watched the cricket match, and in that you might have noticed that whenever a fielder tries to catch or fields a ball, he takes his hands backwards, and there is a reason behind it. That is the application of the Newton's second law of motion. So fielder does this to increase the amount of time while catching a ball. So he, by pulling his hand backwards, he's increasing the time. So fielder is increasing the time, and what happens when the time is increased by, so fielder is increasing the time to catch, or the time of impact of the ball on the hand. So he's increasing the time while catching a ball, and why he's doing so. So while he pulls his hands backwards, he is increasing the time to catch the ball. And when the time, because we know that the force is directly proportional to rate of change of momentum, that is m into v minus u by t. And by increasing this time, we are reducing the rate of change of momentum. This value becomes small. And when this value becomes small, which is directly proportional to the force, the impact of the force is small. So let's try to understand it in this way. Let's say the time is 5 seconds and the rate of change of momentum is 2, so the force is 2 Newton. Now, when we increase this time, let's say we increase this time by 10 seconds. So if we increase the time, so now the force is 1 Newton. So here, when the time is increased, the rate of change of momentum reduces, and the force, it also reduces. When the time is less, the rate of change of momentum increases, and hence the force is more. So in this case, it may hurt the hands of the fielder, but in this case, because the force is less, as the time is increased, rate of change of momentum reduces. So that's why the impact of the force will be less, and hence the hands may not get injured. So in this case, we can say that whenever a fielder catches a moving ball, it actually brings the ball. So if, let's say, the fielder does not pull his hands backwards, so the reason here is that fielder is increasing the time while catching the ball, and which this reduces the rate of change of momentum and applied force. So this reduces the change of momentum, and when this rate of change of momentum is reduced, it reduces and hence force is less. When the force is less, there are less chances of getting hands injured. So there are less chances of getting injured. However, let's say the fielder stops the ball. He does not pull his hands backwards and immediately stops the ball. So in that case, the he's trying to, let's say this is the ball. It's coming towards the fielder's hands, and these are, let's say, the fielder's hands. So he's not pulling the hands backwards. So he brings the velocity of the ball. So this is, let's say, there is some initial velocity. The ball is coming at a speed of 30 meter per second. So by catching the ball and not pulling the hand backwards, he's getting the velocity or reducing the velocity of the ball to zero in a very short time. So this is short, which increases the change in momentum and hence it increases the force and he may get injured his hands. So that's why a fielder pulls his hands backwards while fielding the ball to increase the time while catching the ball, which reduces the change of momentum and hence the force is less and there are less chances of getting injured. Let's move on to the next application of the Newton's second law of motion. Why a high jumper is provided cushion or heap of sand on falling. So reason here is same. So a cushion or a heap of sand is provided to prevent injury to the athlete whenever he falls down after making a high jump. So when athlete falls, let's say this athlete falls on cushion or heap of sand. So now the whenever he falls on a cushion or a heap of sand, this jumper takes a longer time to comes to rest. He takes more time to come to rest because with him, the whenever he lands on the cushion or a heap of sand, so let's say this is the cushion. So whenever the athlete lands on this, so whenever he lands on this with him, the cushions are pressed, and this increases the time for the jumper to comes to rest, and so he takes more times to come to rest, and by doing this, the rate of change of momentum of athlete is less. So which reduces the rate of mm, change of momentum. Now the rate of change of momentum is reduced. So now the rate of change of momentum is reduced. That means smaller stopping force acts on the athlete. So we can say that smaller force, and because it's acts on athlete. Now because the smaller force acts on athlete, so the athlete doesn't get hurt. Okay, so that's the reason a jumper is provided with cushion or heap of sand instead of the mud or let's say the concrete, because when someone falls on a concrete, it takes less time to come to rest. Rate of change of momentum is in that case increased. Larger force acts on athlete and athlete gets hurt. So this is the second, we could say, the application. Okay, how seat belts prevent injuries in car. So how seat belts prevent injuries in car? So let's say in a car accident, what happens in a car accident? So in an accident, so this car strikes some another vehicle or some other obstacle, and a fast running car comes to rest immediately. So this fast running car, this comes to rest in a short time. Okay, so due to this, the large momentum of the car reduces to zero in a very short time. So due to this, because the time is less and the large momentum happens, large momentum is reduced to zero in a very short time. And now when this happens, the seat belts that is worn by the passengers increases the time taken by the passengers to fall forward. So what are the belts doing? So belts, so seat belts, they increase if they are worn by the passengers, they increase the time taken by the passengers to fall forward. Okay. Due to this, now the for seatbelt increases the time taken by the passengers to fall forward, and because of this longer time, what is going to happen? The rate of change of momentum is reduced. So there are two cases. The fast car is in an accident. The fast running car comes to rest. Its large momentum is reduced to zero in a very short time. Now the seat belts, because of this large momentum is reduced to zero in a very short time, there is a large impact on the passengers. If they're not wearing the seat belts, they may get fatal injury, and the seat belts they increase the time taken by the passengers to fall forward. Due to this longer time, the rate of change of momentum is reduced. So the rate of change of momentum is reduced in a long time. This results in low or less injury. We say no or less injury. So that's why the seat belts are provided in to prevent the injury in the cars. Okay, now our last application would be how a karate player breaks slab of bricks in a single move. Okay, here it's because of the very high amount of momentum produced in a very short span of time. So let's try to explain this now. When the hands of karate player moves, they carry velocity. When the hands of this karate player moves, so what are they trying to do? Okay, so the hands of the karate player moves, and you might have seen that they bring down the hands with a very large velocity. So the when the hand touches the, let's say, the slab of bricks or the ice, the velocity is brought down to zero in a very short span of time. So we can say that when the hands touch the slab, the velocity is brought down to zero. Zero with a large amount of momentum in a very short span of time. So what is happening? The hands of the caterpillar moves very fast, or let's say with high velocity. Comes down with high velocity. And when the hands touch the slab, the velocity is brought down to zero with large amount of momentum in a very short span of time. So because of this very short of span of time, the rate of change of momentum is increased, and hence the unbalanced force, and hence we can see very high unbalanced force. This breaks the bricks on the slab. You can see the slab of the ice on the bricks. Okay, so this is how exactly the karate player breaks a slab of bricks in a single blow. So we are done with the Newton's second law of motion and applications. Do like, share, and subscribe. Thank you for watching.